The Pantheon in Rome has stood for 1,898 years. No maintenance beyond basic cleaning. No structural reinforcement. No repairs to the dome. It's made of concrete. Roman concrete. Opus cementitium. The dome is 43 meters in diameter. Unreinforced. Pure concrete. No steel. No rebar. It carries its own weight, has done so for nearly 2 millennia, will likely continue for millennia more. Modern concrete structures begin failing within 50 years, some within 20 years in harsh environments. Interstate 35W Bridge collapsed after 40 years. Modern concrete, steel reinforcement, still failed. Reinforced concrete has a design lifespan of 50 to 100 years. After that, deterioration is assumed. The Pantheon wasn't designed with an expiration date. It was built to last. And it has. This raises 2 questions. Did the Romans know something we forgot? Or did we choose different priorities? The chemistry suggests both. Roman concrete is fundamentally different from modern Portland cement concrete. Different ingredients, different reaction mechanisms, different performance characteristics. Modern concrete is stronger initially, reaches design strength in 28 days, convenient for construction schedules. Roman concrete took years to reach full strength, decades even. Inconvenient for rapid construction. But modern concrete degrades, cracks, allows water penetration. The rebar corrodes. Expansion from rust cracks it further. Roman concrete heals. Cracks seal themselves. Exposure to water strengthens it, especially seawater. We didn't forget how to make Roman concrete. We chose not to. Economics, speed, different optimization. They optimized for permanence. We optimize for initial cost. Both are rational within their contexts, but the Pantheon stands while our bridges fall. The engineering speaks for itself. The volcanic ingredient, Pozzolana chemistry. Roman concrete had a secret ingredient, not secret now, well documented, but functionally different from modern cement. Pozzolana, volcanic ash, specifically from the region around Mount Vesuvius and Pozzuoli near Naples. The name Pozzolana comes from Pozzuoli, the primary source of this volcanic ash. Volcanic ash. Composition. Silicon dioxide, SiO2, 45 to 55% by weight. Reactive silica. Critical component. Aluminum oxide, Al2O3, 15 to 20%. Contributes to bonding. Calcium oxide, CaO, 8 to 12%. Reacts with water. Iron oxide, Fe2O3, 5 to 8%. Provides some strength. The key is the reactive silica. It's amorphous, not crystalline. This means it's chemically reactive. On the Pozzolanic reaction, mix pozzolana with lime, calcium hydroxide, CaOH2, and water. The reactive silica in the ash combines with calcium hydroxide, forms calcium silicate hydrate, CSH. This is the primary binding compound. It's what holds Roman concrete together. The reaction is slow, takes weeks, months, years, continues as long as moisture is present. Roman concrete gains strength over time. The longer it sits, especially in humid environments, the stronger it becomes. Modern Portland cement, invented 1824, Joseph Aspdin, England, named after Portland stone, which it resembles. Composition: limestone, calcium carbonate, and clay, aluminum silicate, heated to 1450 degrees Celsius. This creates calcium silicates, primarily tricalcium silicate, C3S, and dicalcium silicate, C2S. Add water. Hydration reaction occurs. Forms calcium silicate hydrate, Same CSH as Roman concrete. But the reaction is fast, reaches 70% strength in 7 days, 95% in 28 days. Convenient for construction. However, the reaction essentially stops. No continued strengthening. The concrete is what it is after 28 days. The critical difference. Portland cement fights nature. It's designed to set quickly, harden rapidly, resist water once cured, but it's brittle. Cracks under stress. Those cracks allow water penetration. If rebar is present, corrosion begins. Roman concrete reacts with nature. The Pozzolanic reaction continues indefinitely given moisture. Cracks that form allow moisture in. The moisture triggers more Pozzolanic reaction. The crack heals. One is static. One is dynamic. Both work initially. Over centuries, dynamic wins. Marine environments. This difference is most pronounced in seawater. Saltwater is catastrophic for modern concrete. Chloride ions from salt penetrate, reach the rebar, initiate corrosion. Rust expands. Concrete cracks. Accelerating failure. Modern marine concrete structures require constant maintenance, cathodic protection, coatings, sealants, inspections. Roman marine concrete structures? Still standing. Sebastos Harbor in Israel, built 25 BC, underwater concrete breakwaters, 2,000 years, still intact. The seawater doesn't destroy Roman concrete, it strengthens it, through a different mechanism we'll address shortly. The MIT discovery, hot mixing and lime Clasts. MIT researchers publish findings, analysis of Roman concrete samples using advanced imaging. They found something unexpected. Small white chunks throughout the concrete. On lime Clasts. For decades, these were considered evidence of poor mixing. Romans didn't mix their concrete well. Lime lumps remained. The MIT team proved otherwise. Those lime clasts were intentional, critical to performance. The traditional assumption. Roman concrete was made by mixing slaked lime, calcium hydroxide, with pozzolana and aggregate. Slaked lime is produced by adding water to quicklime, calcium oxide. Controlled process. Creates uniform paste. Traditional assumption. Romans used slaked lime, mixed it with ash and aggregate, created concrete. The hot mixing revelation. MIT analysis showed the lime clasts were quicklime, calcium oxide, not calcium hydroxide. This means Romans mixed quicklime directly into the concrete, without slaking it first. This sounds wrong. Quicklime reacts violently with water. Exothermic reaction. It releases heat, creates steam. Why would you add this to concrete mix? Seems dangerous, unpredictable, poor practice. But the evidence is clear. The lime clasts are quicklime derived. They exist throughout Roman structures. The hot mixing process. Add quicklime directly to the mix. Add water. Violent reaction occurs. Temperature spikes to 200 to 300 degrees Celsius locally around quicklime particles. Steam generation. Turbulent mixing. The heat and turbulence create two effects: better distribution of lime throughout the mix, and residual quicklime pockets. These pockets don't fully react. They remain as lime clasts, high calcium islands in the concrete matrix. The self-healing mechanism. Over time, the concrete cracks. Inevitable. Thermal expansion. Settling. Stress. Water enters the crack. Reaches a lime clast. The quicklime reacts. Forms calcium hydroxide. This calcium hydroxide is supersaturated, unstable. It precipitates as calcium carbonate, limestone. The calcium carbonate fills the crack, seals it, prevents further water penetration. This is autonomous self-healing. No human intervention. The material repairs itself. The reaction continues as long as unreacted lime clasts exist, potentially centuries. Experimental validation. MIT team created concrete using hot mixing method, incorporated quicklime directly, created lime clasts. They induced cracks, exposed to water, monitored healing. Result: cracks up to 0.6 millimeters sealed completely within 14 days. The calcium carbonate precipitation filled the gaps. Control concrete made with slaked lime only. Cracks remained open. No healing observed. The lime clasts are the key. They're a distributed repair mechanism embedded in the material. Why modern concrete doesn't have this? Portland cement production eliminates calcium oxide. It's fully reacted during manufacturing. Modern concrete has no unreacted lime reserves. Nothing to fuel self-healing. Cracks stay cracked. Water penetrates. Rebar corrodes. Failure progresses. We optimized for rapid strength gain. Lost the long-term resilience. Engineering trade-off. Romans didn't have rebar to protect. So water penetration wasn't catastrophic. Actually helpful for continued curing. We added steel for strength. Created vulnerability to corrosion. Water became enemy instead of ally. Different material systems. Different failure modes. Different longevity. The seawater paradox. Tobermorite crystal growth. Seawater destroys modern concrete. This is well established. And chloride attack, sulfate attack, aggressive environment. Marine structures require special concrete mixes, protective coatings, sacrificial anodes, continuous maintenance. Roman concrete in seawater grows stronger, measurably, over centuries. The mechanism was discovered through analysis of Roman harbor structures, particularly Portus Casanus and Portus Iulius. Tobermorite formation. Tobermorite is a rare calcium silicate hydrate mineral. Formula CF5Si6016, open parenthesis, OH, close parenthesis, 2 times 4, H2O. It forms only under specific conditions. Elevated temperature or prolonged seawater interaction with volcanic ash. In Roman concrete submerged in seawater, Pozzolana reacts with calcium from lime, with silica from the ash itself. Seawater provides additional calcium and alkali ions, magnesium, sodium. These modify the reaction environment. Over decades and centuries, Tobermorite crystals grow within the concrete matrix, particularly in voids and cracks. These crystals are highly stable, resistant to degradation. They interlock with the existing CSH gel. The result: the concrete becomes denser, stronger, less permeable. The seawater improves it. Documented evidence: core samples from Portus Casanus, Roman harbor, Tuscany coast, built 1st century BC, analysis by UC Berkeley and Italian researchers. Published 2017 in American Mineralogist. They found extensive Tobermorite formation, crystals growing in cracks, filling voids, binding the matrix tighter. Compressive strength measurements increased by 20 to 30% compared to estimated original strength. The concrete literally got stronger over 2,000 years of seawater exposure. Tobermorite. A related mineral. Tobermorite, aluminum-substituted tobermorite, also forms. This occurs when aluminum from the Pozzolana incorporates into the crystal structure. Tobermorite is even more stable than regular tobermorite, more resistant to dissolution. It forms in seawater through complex reaction between pozzolana, lime, and seawater components. The crystals grow slowly, very slowly, nanometers per year, but over centuries, substantial formation occurs. Modern concrete. In seawater, modern Portland cement. Concrete does not form Tobermorite in seawater. Different chemistry. Instead, seawater attacks it. Chloride ions penetrate, reach rebar, initiate corrosion. Sulfate in seawater reacts with calcium, aluminate in cement. Forms ettringite, expansive mineral, causes cracking. Magnesium in seawater reacts with calcium hydroxide. Forms magnesium hydroxide. On weaker than original compounds. All these reactions degrade the concrete, reduce strength, increase permeability, accelerate failure. Typical marine concrete lifespan, 50 to 75 years in harsh environments, even with protective measures. Roman concrete, 2,000 plus years and counting, still structurally sound, still functional. The protective mechanism. The Tobermorite acts as a protective barrier. It's highly impermeable, blocks further seawater penetration. As it forms in cracks and voids, it seals the concrete, makes it denser, more resistant. This is the opposite of modern concrete behavior. Modern concrete degrades. Roman concrete improves. The longer Roman concrete sits in seawater, the better it performs. Self-improving material. Modern engineering hasn't replicated this. We know the chemistry, we understand the mechanism. But replicating it requires volcanic ash from specific sources. Lime instead of Portland cement. Slow curing, economically unfeasible for most applications. So we accept 50-year lifespans. Plan for replacement. The engineering choice. Permanence versus profit. Roman concrete superior? In longevity, yes. In initial strength, no. In construction speed, definitely not. Portland cement concrete reaches design strength in weeks. Roman concrete takes years. Portland cement can be manufactured anywhere. Limestone and clay are common. Volcanic ash is not. Portland cement is standardized. Predictable. Quality controlled. Roman concrete varied by ash source. We didn't forget Roman concrete. We chose differently. Economic rationality. Modern construction economics favor rapid turnover. Build. Use for 50 to 100 years. Replace. This generates continuous demand, continuous employment, continuous revenue for industry. Building structures that last 2,000 years? Economically irrational. No replacement market. No future contracts. Romans didn't think this way. They built imperial monuments, symbols of eternal power. Permanence mattered. Different incentives, different outcomes, both logical within their contexts. Modern research. Some researchers are developing self-healing concretes, incorporating bacteria that produce limestone, encapsulated polymers. Others are exploring Roman-inspired mixes, using volcanic ash where available. Supplementary cementitious materials, fly ash from coal plants, slag from steel production. These partially replicate Pozzolanic behavior, but none match Roman concrete's complete performance profile, the lime clasts. At the Tobermorite formation, the centuries-long improvement. We understand the chemistry. We could replicate it. We choose not to. Economics override engineering elegance. The accounting problem. Concrete with 50-year lifespan is an accounting asset. Depreciation schedule. Replacement planning. Budgetable. Concrete with 2,000-year lifespan is an accounting problem. No depreciation. No replacement budget. Eternal liability. Modern financial systems prefer predictable replacement cycles. Roman permanence breaks the model. So we build temporary, plan for failure, accept degradation. Call it modern engineering. The Pantheon doesn't care about depreciation schedules. It stands. It will continue standing. Our bridges crack, our buildings crumble. We rebuild. The cycle continues. Both systems work. One creates jobs through replacement. One created monuments through permanence. We chose jobs. They chose monuments. The monuments remain. The jobs continue. Neither is wrong. Both serve their society's values. But only one produces 2,000-year structures. The chemistry is published. The mechanisms are understood. The materials exist. We could build like Romans. We choose not to. That choice, more than any forgotten knowledge, explains the difference. Welcome to modern engineering. Temporary by design. Profitable by deterioration. Rational by economics. The Pantheon stands as witness, not to forgotten knowledge, but to different priorities, different values, different definitions of success. Concrete that lasts forever versus concrete that employs indefinitely. Choose your metric. Both are valid. Only one produces ruins that outlast empires.